Remember we had a disk of charge and we found the electric field some distance above, and then we made the assumption that the radius of the disk goes towards infinity, and we found the electric field was a constant value. Okay. And so we calculated the electric field was sigma over 2 epsilon naught. Okay, but we did that with a series of very complicated integrals, we had to do those integrals and then take the limits, and that became kind of complicated. And so we know that Gauss's law gave us a simple way of solving problems with the case of the cylinders and the wires and cylindrical symmetry. So let's see if it makes this any easier. And so we imagine that we've got a surface here. Okay, so this is a side view of the surface here. Okay, top view, it might be something like that. We got some charge here. Okay, and so we know that by symmetry, if it's very big, so in other words, if the ends of it are a long ways away, then the electric field goes straight away from it. Okay, so what I want to do is figure out something that would be symmetric with that. Well, it's like a little pillbox or something. So it could be a cylinder or a cube or something, so that this is some distance, h above, and this is some distance h below. Okay, so we know the electric field at the top and the electric field at the bottom should both be basically the same. And so we're going to say now that the integral E dot dA equals enclosed charge over epsilon naught. So that's going to be integral E dot dA for the top plus the integral E dot dA for the bottom plus the integral E dot dA for the side. And that's going to be the enclosed charge over epsilon naught. Okay. Well, the side one's easy. The electric field is perpendicular to the sides, so, or rather, it runs parallel to the sides. Okay, it runs parallel to the sides, so the area vector is perpendicular to the electric field, and therefore that is 0. The top and the bottom, the electric field is constant, so it comes out of the integral. The dot product goes away because the area vector and the electric field are in the same direction, so that's just going to be, this becomes EA of the top plus EA of the bottom. Well, assuming that our surface is symmetric, those are the same, okay? And Q, it's just going to be sigma times A over epsilon naught. Well, that means that 2EA is sigma A over epsilon naught. The A's cancel, and so E equals sigma over 2 epsilon naught. Done. Okay. And so once again, we got the exact same result that we did with all the nasty integrals, but Gauss's law allowed us to shortcut some of the difficult things that we were doing. And so, again, this is one of the powers of Gauss's law, one of the things it can do for us. And so that turns out to be a very, very useful sort of thing. Okay.